if you're in the plane and you have like the vorticity in the plane, that's a two-dimensional field, and you treat it as a random field, a Gaussian random field. So you specify a covariance operator on it, correlation operator. Then basically, depending on the regularity you're imposing by this covariance operator, you get very different classes of fields. Now there's something I've been, this is buckling. But of course, if you only, this is something really confusing, right? Because actually, if you only look at a finite dimensional projection of that, and you look at the statistic of this, then you finite dimensional again, and then actually things start to look fine again. And obviously, often we just look at 2-point statistics or something like this, and then you're looking at finite dimensional section of the whole thing, and then things start looking okay again. Anyway, so this is just something to keep in mind. All right. Right. But in finite dimensions, if you start with Gaussian, any other Gaussian is absolute continuous with respect to another Gaussian. So basically, in finite dimension, you don't need to worry. You start with one Gaussian. As long as if you have enough data, it will go down to the right value. You have contraction properties. Asymptotically, it will all look like a Gaussian, et cetera, et cetera. So this is all fine. But as I said, there are some dangers if you go to high-dimensional spaces. It becomes very high-dimensional. OK, so this is one thing. This is, as I said, very essential. Now, another thing, you need to talk about distances. Now, in Rn, we have the Euclidean distance and other distances. But the Euclidean is probably the one that's the most widely used. You also wanted to compare measures. Because even if everything concentrates on a circle, let's say in this high dimensions, this hypersphere, the surface of a hypersphere, then on that hypersphere, of course, you can still have different measures, so all absolute continuous, and you try to get a distance measure. You want to know how far they're away. And that will actually serve then later on to characterize also the efficiency of Monte Carlo methods. Because the cursive dimensionality is easiest being seen in that these two things get sort of not close together anymore, and then the whole thing becomes complicated. And so one measure of distance is the Kullback-Leibler divergence. The divergence is you basically take two measures, or two densities or whatever. And you take the log. This is basically a Kullback-Leibler. This is a Radon negative derivative. So it's maybe just the ratio of the two densities. And then integrate it, taking the expectation value. Yeah?
This isn't the actual distance measure, right? It's missing symmetry, right?
Yeah, right. I just wanted to get to this. So it is sort of a, that's why I call it a divergence. It's not a proper distance like you know from the Euclidean, because first of all, it's not symmetric. If you switch it, you see it's not quite, doesn't give you the same thing. But you can make it symmetric. You just can take the other version of this and add it together, and then you have a symmetric version. That's not the big problem, but the triangle inequality doesn't hold. So triangle inequality. But still, it is a very widely used sort of measure for telling you how far things are apart in the measure. And it has a nice property. It's non-negative. That's important. So this is something it inherits from a distance. And it's zero exactly if and only if the two distributions, measures, or whatever are equal. Only then it's zero. So this is what matters in this context. And you can equally replace this by saying, you can rewrite this by saying that, that you split this up essentially into this is, as I said, this is This is the likelihood, which is here essentially. I mean, this is the Radon negative derivative. It's the likelihood here. So basically, you're taking the expectation of the likelihood. This is like a loss function. So physicists really like this stuff. So and machine learning people also, because a lot of machine learning people come from statistical physics. So this is like a loss function. That's sort of telling you how well your distribution fits the data. And of course, the distribution that fits the data best is just the function that actually sits exactly on the data. So that would minimize the loss. But of course, this you cannot do because you also have a regularization. You have a penalty term that you should not move too far away from your prior in a way. So the prior is like an anchor that keeps you sort of hooked to. And so you basically, the posterior distribution can be seen as the distribution that minimizes or balances these two things and minimizes the quantity. And minimization principles are always good. Like think of 4D var. Not everyone likes 4D var, as we heard, but it's also using a minimization problem. We'll come back to this. So this is like a minimization principle on the level of densities. And the minimizer is actually the log of, again, of this quantity we most often ignore. That was the evidence, the normalizing factor in Bayes' law, right? That tells you how well the model fits. And that's called the free energy. In physics, it's called the free energy. So this is the expected loss. This is, again, the Kullback-Leibler now between the distribution we're seeking and the prior. And as I said, it can be, this Bayes principle can be understood as a minimization over this functional. Okay. So now, I mentioned machine learning already a few times. And of course, we all know deep learning and all this being around. So you have to ask yourself, what are we doing here? I mean, is data assimilation just another incarnation of it? What is different? And can we maybe also contribute to this, to machine learning in a more general context? And both fields, to a large extent, are Bayesian. And they have data and they have quantities of interest to estimate. In a neural network, that would be the weights of the neural network. And you learn it by showing it data. And so basically, it's sort of about the same thing. And you want to compute posteriors. I think one of the main differences is that in machine learning, the dimension of the data is very high relative to of the quantities of interest, right? So a neural network is trained on an incredible amount of data, and there are many weights, but the weights are still finite. There are finitely many layers, finitely hidden layers, hidden units, et cetera, et cetera. So that's why I guess it's called big data. We're not doing big data, my opinion. You might object, but I think we're not doing big data because actually, in our case, the dimension of the models is infinite dimensional, so PDEs, and you want to resolve it in time. So it's actually multi layers of infinite dimensional fields you want to estimate. And you have a lot of data, but relatively speaking, the data is still limited. And certainly in climate reconstruction, it's tremendously limited. But we can still do things, but it leads to different type of algorithms. And it's actually interesting to talk to machine learning people because they really, for example, they often work much more on this bit to make that efficient. It's a little bit like Greg's talk yesterday where he said, well, what is the most efficient way of using data? For them, that's really crucial because they don't want to really work on these huge data sets. They want to reduce the data, et cetera, et cetera. So they work a lot on this, whereas we, in a way, much more on this here and working on the fact that this is very high dimensional. Then machine learning is primarily on, so far, it's changing static inference, so the network's not changed in time. You adjust the parameters and that's it. So one thing I really like about data assimilation, it has a forgetting factor. It's crucial, right? Chaotic systems forget where they are. And forgetting is huge for also for us humans. I mean, I really have a bad memory. I mean, I can't memorize names and all that. And of course, often that's pretty painful and embarrassing. But often it's also really helpful. I mean, I can't remember bad things after a couple of days and then wake up happily and think, oh, it was all fine, right? So anyway, so forgetting is an important factor of learning. And I think it's one thing why, for example, parameter estimation is so much harder than state estimation, I believe. One thing. I mean, the other, because there's no natural dynamics, there's no natural forgetting. Of course, people then add some sort of random dynamics to add forgetting. But both, of course, lead to huge minimization problems, and quantification of uncertainty is a big issue, right? You just don't want not just a number, but you want to have a distribution. Of course, that's also one reason why 4D VAR is maybe not as popular anymore, or the extension now that also use ensembles. So you don't just want a best estimate in a certain way, but you also want to know what is sort of the spread around it. In fact, I believe that the methods that have sort of become so hugely successful in data assimilation can be seen as clever ways of doing optimization without derivatives. And I think that's something that's going to be intriguing to a lot of communities. I think that we have these very clever methods. So you basically use the ensemble to do finite difference approximations to derivatives, and it naturally gives you. And it comes from the fact that you lifted this optimization problem up to the level of densities. It makes the thing much harder in a way, but it also gives you a lot of benefit. Because when you work on the level of densities, you don't look at derivatives directly anymore, but implicitly you're still minimizing. Plus you get additional information on the uncertainty. I think this is a fantastic generalization, and data assimilation has come up with fantastic algorithms, the ensemble Kalman filter, in many cases, to get really good approximations. So these are derivative-free inference techniques or minimization techniques. Okay, right. Okay, computational approaches. Just general. And of course, I'm not going to be complete. I just want to address those that will be relevant later as well. So there are two, largely speaking, you can say two classes. The one are deterministic. So there's no random number drawing involved, no ensembles, nothing. And then there are the Monte Carlo methods that involve an element of randomness. And so I guess most of you seen also in the hand-on sessions, there were at least the 3D VAR is clearly a minimization technique. You write down your cost functional. Actually, you don't need to talk about probabilities whatsoever. You just you write down a cost functional, and we heard several times that there are various ways how to look at this, these squares, etc. And then you minimize this function, and you're done.